Hi, welcome to a lecture on approximations for fully sampled electrically large apertures. And here we're talking about large planar arrays of the type shown on the left here, for which the design parameters are nx, the number of elements in the x direction, separated with spacing dx, and ny in the y dimension with element spacing dy. Now the physical area of this aperture in which the array exists is approximately nx dx ny dy, and this is approximate because it depends on whether you measure from element center to element center on the edge elements, or whether you allow some additional margin on the edges. Obviously, this distinction becomes less important as the array becomes larger and larger. And what we mean specifically by electrically large is that the overall x dimension is much greater than wavelength, and the overall y dimension is much greater than a wavelength. Now, addressing the fully sampled part, what we're saying here is that dx and dy are assumed to be less than or equal to the critical spacing. And what we mean here by critical spacing is the smallest spacing for which the directivity and the effective aperture are proportional to the number of elements in the array. The specific dimensions in terms of wavelengths depend on the elements. For low-gain elements such as dipoles and patches, we're talking about spacings between 0.3 and 0.9 wavelengths, with 0.5 wavelengths being a common value. We established in a previous lecture that for a planar array, which is both electrically large and fully sampled, that the effective aperture of such an array is approximately equal to the physical aperture of the array when we have broadside incidence. And that subsequently, the directivity, which is always given by 4 pi over lambda squared times effective aperture, is 4 pi over lambda squared times physical aperture. And this is obviously a remarkable simplification because effective aperture is relatively difficult to compute, whereas physical aperture is easy to compute. Note that the aperture does not need to be rectangular for this to be true. All that's needed is for the aperture to be electrically large and fully sampled, and that the criteria apply in any dimension. So here it was simple because it's rectangular and there's two principal directions in a rectangular aperture. But you can see that the same argument could easily be made for elliptical apertures as well. Okay, so this is all for broadside incidence. And so you might ask, what about directions other than broadside? Well, here the fact that an electrically large, fully sampled aperture can be interpreted as an optical structure is useful. This is addressed in a different lecture, but the idea is that when we have an array which is electrically large and represents a fully sampled aperture, it behaves like an optical structure in the sense that the amount of power that is captured is similar to that of a window. So the idea here is that you imagine this physical aperture, and there's an instant power density from broadside, that's so many watts per square meter. Watts per square meter, the power density, times the physical aperture, is the power captured by an aperture. If you follow that thinking through, then you see that if you turn the aperture so that now the instant power comes from a direction off broadside, and here that angle is psi, then the power captured using the optical paradigm would be the power density times the physical aperture times cosine psi, which is 1 when psi is 0, as the case on the left, and 0 when psi is pi over 2, which is the case where the incident power is incident from the plane of the aperture. So this is obviously true for a structure which is behaving optically, and so we say that the effective aperture is, to a good approximation, equal to the physical aperture times cosine psi. This breaks down when psi is close to pi over 2, that is the end-fire direction, because the projected area is not necessarily electrically large in this case. In other words, the aperture through which the power can arrive is this distance I'm now indicating, and as that approaches end-fire, that distance shrinks. And eventually, that distance is no longer going to be electrically large. And once it's no longer electrically large, then it can't be optical. So, in that case, the element pattern will become important. So there is a range of angles around pi over 2 for which we can't use this approximation. And those angles correspond to the angles for which this projected distance is no longer electrically large. Now this all applies in the transmit case as well. In transmit, such arrays can be treated as continuous sheets of current, and it's often easier to calculate receive performance by instead calculating the transmit performance via reciprocity. The effective aperture is equal to the directivity on transmit times lambda squared over 4 pi. Another approximation of interest is that for half-power beam width for the main lobe. And in a previous lecture, we've worked this out. So I'm going to skip over the details here and simply remind you what the idea is. The idea is that the distribution of current in an aperture is related to the pattern through a two-dimensional Fourier transform. So if the distribution of current is uniform across the aperture, we end up with a sinc pattern. And we can use this relationship to get a value for the angle at which the first null occurs. That is right here. And that turns out to be simply 1 over the electrical length in that dimension. So then with some additional relatively gentle approximations, we end up with an expression for half-power beam width being roughly 57.3 divided by the electrical length and wavelengths for that plane. Or you might say it's 60 degrees divided by the size of the aperture and wavelengths. Very convenient expression to know. Do not forget, as many do, that this is approximate, for starters, for a fully sampled and electrically large aperture. In other words, this aperture has to work like a current sheet for this to be true. In addition to the fact that it has to be for a uniform distribution, generating a beam which is broadside to the aperture. So despite all those caveats, this is a very useful rule of thumb for analysis and design. In particular, it's a useful way to get started with the design because this tells you for a certain half-power beam width how big the array is going to have to be in that plane. This kind of thinking yields some relatively useful additional insights. For example, the half-power beam width must increase as the beam pointing moves away from broadside. Now, how do you know that? Because the effective dimension is the projected dimension, and as the beam moves away from broadside, that projected dimension is being reduced by that factor cosine psi. So as that projected dimension is decreased, the half-power beam width must be increasing. So we know from just this much that we expect the half-power beam width to increase as the beam points away from broadside. Now returning to directivity, it's useful to have an approximation for the directivity of these arrays. And we've already established, of course, that the directivity is approximately equal to 4 pi over lambda squared times the physical aperture with the caveats indicated above. So for a rectangular array, we have directivity is equal to 4 pi over lambda squared times the two principal dimensions in the x and y directions. Well, what if these simplifying approximations don't necessarily apply, but the array is electrically large and you know the half-power beam width in the two principal planes? In other words, now I'm asking the question, what happens if you know something about what the half-power beam width is? Is it possible to compute the directivity? Is it possible to get a shortcut calculation of the directivity, approximate it may be, if you know the half-power beam width, which is relatively easy to get? Well, the answer to that question goes like this. If you know the half-power beam width in one plane, say the E plane, and then you know the half-power beam width in an orthogonal plane, say the H plane, well, then we can ask, what do we know about the beam solid angle? Well, beam solid angle in general is given by this expression, 1 over 4 pi, integrate over a sphere of the normalized power pattern. But this is essentially a calculation of the solid angle of the subtended beam, which is very narrow if the array is electrically large. And a rough guess of the solid angle would simply be the half-power beam width in two orthogonal planes multiplied together. That would give you radians squared, which is essentially steradians, again, in the sense of a rough approximation. So if you accept that the beam solid angle is roughly given by the product of the half-power beam widths in two orthogonal planes, then you can now apply the exact expression, directivity equals 4 pi over beam solid angle, to get this result, that the directivity is roughly equal to 4 pi radians squared divided by the half-power beam width in those two orthogonal planes. Now, it's more often expressed in degrees, and if you convert this to degrees, you get directivity is approximately equal to 41,000 degrees squared divided by the half-power beam widths in two orthogonal planes multiplied together in degrees. And I'll point out that if you see this in antenna textbooks, you will see a range of possible values here. 41,000 is actually probably the highest value you'll see. You'll see various smaller values such as 32,400, 26,000, and 23,000. And this results from various refinements. For example, the expression I came up with that yielded 41,000 simply assumes that the beam looks like this. But in fact, the beam is probably elliptical. And so if you do that conversion, 41,000 becomes a smaller number. Various other refinements will give you successively smaller and smaller numbers. So, in fact, it's somewhere between 23,000 and 41,000. That's a difference of roughly 3 dB. So, for an array which has a very high directivity, 20, 30, 40 dB, that 3 dB difference is relatively small. And again, the principal value in this approximation is to get started or to figure out a rule of thumb kind of calculation that facilitates design. And then, of course, you would follow this up with a more rigorous calculation once you have a design candidate in mind. That concludes this lecture on approximations for electrically large, fully sampled arrays.